Today, we're going to learn a couple more ways to prove that triangles are congruent. This first one refers to any triangle. The second method we have, or theorem, first one's a postulate, the second one will be a theorem, refers only to right triangles. SAS, what does that mean? Side, angle, side. In other words, if we have two sides and the angle in between, that's called the included angle. And it makes a difference. You can't just say that two sides and any old angle are congruent. That won't work. The angle between the two congruent sides, that's what works. Why is that? Well, suppose we do this. We draw ourselves a triangle with an angle and two sides equal. Now, the angle, let's draw another triangle down here, I guess. We'll say that this angle equals this angle, this side equals this side. Now, watch. We'll draw a line here. And another one here. These two are exactly the same length. See what happened? These are the only two possibilities, though. So, if you have two sides and some outside angle are congruent, you could say there's a 50-50 chance that the two triangles are congruent, because with this angle and these two sides congruent, it could look like this, or it could look like this. Either one would work. Which is why there's no such thing as the angle side-side postulate or angle side-side theorem. Because it's not true. We can have two different triangles which both have two equal sides and one equal angle. The catch over here is that congruent angle has to be between the two congruent sides. See? Well, I just got done saying that side-side angle or angle side-side doesn't work. And now here we have a right triangle theorem, which is in fact angle side-side. What's up with this? Well, the catch is it's a right angle. Remember I drew that little thing over here? Well, suppose I did it again. But this time it's a right angle. Well, if this side, and now we're going to draw in this side. And we do it again down here. See if I can draw pretty much the same thing. These are both right angles. Before, when this leg extended out here, I could drop it down this way, or I could drop the other one down this way, and it would be the same length either way. So I had two possibilities for a triangle that had two congruent sides and some other angle congruent. But for a right triangle, that's not true. There's no other way to drop this. I could put it over here, but that would be a whole different triangle. So if you've got a right angle here, the two ways to swing this arm don't exist. What I have to do is, if I'm out like this here, and this is the congruent angle, now I can swing this arm down here, or I can swing it out there, same length. But yet the triangles aren't congruent, even though this and this would have the same length. Here I can't do that because of the right angle. That's why it works. So if you restrict this to a right angle in this very narrow, specific case, you do have congruence implied by, in a sense, two equal sides. It's actually the hypotenuse and a leg. Why? Well, suppose it was two legs that were congruent. what would you have? Well, that would just be the side angle side theorem we just talked about a minute ago, wouldn't it? This is just a special case of that. The fact that the angle in between the included sides happens to be a right angle is kind of irrelevant. The point is they're congruent. So, for right triangles, you could say there's a leg-leg theorem, because if the two legs are, this leg is congruent to this leg, and this leg is congruent to this leg, then the triangles must be congruent, because we already know the angle in between is congruent by the fact that it's a right triangle. So that's a leg-leg theorem would be kind of redundant. But this isn't, because this is a side-side angle, which in general is not true, but for a right triangle it is, where this side here is actually the hypotenuse and this is the leg, and that's why it says HL over here rather than SS, hypotenuse and leg, because in a regular old triangle we call these sides. There's a side, and if I draw something down here that would be a side. Right triangles have their own terminology. The side opposite the right angle, that's the hypotenuse. The other two, those are the legs. That's just how we talk about right triangles. And having a specific case for just one little type of triangle might seem kind of weird. I mean, why not have special theorems if this were a 60-degree angle, and another set of theorems if this were a 30-degree angle? Well, the reason is that right triangles are super important. Double super important. They're all over the place. They form the basis for all kinds of things. Pretty much trigonometry, which is kind of big, right? Also, well, everywhere. I mean, heck, take a look at your table. If you had a table and the legs don't come out at 90 degrees, since the force goes straight down like that, you're kind of messing yourself up if you have a leg go off like that or like that. You're putting extra forces on the joint here that don't need to exist. So they end up being right angles, and you'll see that all over the world. In man-made structures anyway. I don't know about nature how often it uses right angles. Right triangles are all over the place. And if there's any single triangle that is more important than any other, it would be the right triangle. That's a big one. We're going to use it a whole bunch in this course. I guess another reason that right triangles work out so well is that they fit together well. Notice rectangles fit together pretty well. It's not that easy to make pentagons and hexagons fit together. But rectangles, yeah, they stack real easy. For instance, if you are putting your walls on a house, you usually want them at right angles. Makes things work out much more simply and easily. And then if you add a deck, you use things you know about right triangles, which we will learn later, in order to square it, so that you run your deck off perpendicular to the side of the house, and then square off the corners of the deck, so it doesn't look like some sloppy mess that somebody just dropped down by accident or something. To do that, you produce right angles. Like I say, right angles and right triangles are super important. Now here's one that it's kind of long and complicated. You just glance at it, but we go through this one letter at a time. That's probably not that bad. In fact, one thing we might do to simplify this, there we go. Now we got a little better picture of what it is we're talking about here. Now, which of these does not, the important part there, does not allow you to conclude that these two triangles are congruent? Well, let's see here. AB is congruent to DE. That's this side and this side. Well, that's a good start. BC is congruent to EF. That's this side and this side. Angle B is congruent to angle E. So we have this side, these two sides are congruent to these two sides, and the angle in between, the angles in between are congruent. Oh, that's our SAS theorem, isn't it? So we could say they're congruent based on this. AB is congruent to DF. Maybe congruent to DF, okay. Yeah, just mark it to show that they are okay. AC is congruent to DE. And angle C, that's this one here, is congruent to angle E. Well, this looks like side-side angle. Remember, I showed you just a few minutes ago that that doesn't work. Or you could say angle side-side. Unless you've got a right triangle, that doesn't work. So it looks like this is probably the answer. But let's check out the other two just to make sure. Now I removed the marks that showed congruence, because we're going to work with a whole another set of congruences here. AC is congruent to DF. Okay, there we go. BC is congruent to EF. BA is congruent to DE. It seems like they just restated what they put in Part A in a different order. In other words, side, side, side. The three sides are congruent, so this would imply that they were congruent. So B is still looking like our best choice. Now I remove those congruence marks, and we'll check this one out. AB congruent to DE. Yeah, this is okay. AC is congruent to DF. Just mark those two. Angle A is congruent to angle D. And when I said that this was kind of a rewriting of this, I was wrong. Once again, what are the odds? This just says that all three sides are congruent. This is two sides and an angle are congruent. Don't ask me what I was thinking when I said that. I guess I probably just wasn't. This is not just a rewrite of this. They're different things. If you were throwing pencils and paper at the screen when I said that, I don't blame you. Just hope you didn't do any damage. This one would show that they were congruent. Well, again, once again, we've got the, oh, I'm sorry, this is not right. We should put two hash marks there to show that they're congruent. Wow. That's it. And once I make a mistake on a problem, I'll make 5 more. You better watch me closely. I'm dangerous. So that B did turn out to be the one that just doesn't work. And why was that again? Maybe I should, well, AB and DF. These two, well, that's kind of a mess. I shouldn't do it that way. This is the one that said AB and DF are congruent. AC and DE and then angle C and angle E. And you can see the problem. It's the outside angle, just like I said before. So B is definitely the correct choice. Okay, here's a nice one. Decide whether the information is enough to prove that the triangles are congruent. And the only real information we have is that Z is the midpoint of PY and x cubed. So right off the bat we can go, since C is a midpoint, it breaks them up into two congruent sections. This is congruent. Ooh, pardon me. There we go. This is congruent to this, and this is congruent, these two. In other words, PZ is congruent to YZ, because Z is the midpoint. What about these two angles here? Well, these are vertical angles, so they must be congruent. So what do we have here? We have a side congruent to a side, another side congruent to a side, and the angle in between is congruent. So, looks like side angle side to me. And the answer is, you can prove they're congruent, and side angle side is the one you would use to prove it. Here's one where, some dumb guy who makes geometry videos messed up. What did he do wrong? Well, you need to know something about the relationships between these sides before you can set up any equations that will accomplish anything. It'd be very useful if these two triangles here and here turned out to be congruent. Well, wait a minute. This is 4x and this is 4x. So these two sides are congruent. This side here, well, it's congruent to itself. So we have a side and a side that are congruent. Oh, and the angle in between is, so we got side, angle, side. These two triangles are congruent. So we can definitely set up an equation. That's not what he did wrong. However, if this side is congruent to this side, and this side is congruent, of course, to itself, it's this side and this side that are congruent. He set it up so that this side was congruent to this side. That's no good. You have to match things up right. This side's congruent to this side. It's like this. So, boom. And he set this equal to that. That's no good. So, that's about all there was to it. That's a little bit strange. I mean, I had to think about it for a minute. It wasn't obvious to me, but then you got to spot that these two sides are equal because they're both given as 4x. Once you've got that, sides are always congruent to themselves. So once you know the two triangles are congruent, it's real easy to work this out. And it's real easy to see that this is a mistake. Well, here's one where I'm pretty sure we have enough information. We might even have more than we need. Let's check it out. These two are isosceles triangles. That helps. We know that two sides of an isosceles triangle must be congruent. So the base is Kn for one isosceles triangle. So this isosceles triangle has a base of Kn. So here's the two legs. They must be congruent. The other one has a base of Mn. So here's the two legs for this. Uh-oh. This one must be congruent to this. You see, this leg here is doing double duty. It's a leg for this isosceles triangle. It's a leg for this isosceles triangle. And NL bisects angle KLM, which by definition means that it's broken it up into two equal angles. This angle equals this angle, and this angle equals this angle. Is there enough information to prove this congruence? Well, let's see here. The fact that this angle equals this angle I think that's probably extraneous. That might have been part of what I meant when I said I think we have even more information than we need. This angle is congruent to this angle. This side is congruent to itself. And these two are congruent. These two wound up being congruent through a sort of I guess you'd call it a graphic demonstration of transitivity. Because this one's doing double duty. And they're both isosceles. This has to be congruent to this, and this has to be congruent to this. So, boom, these two are congruent through the transitive property. So, if I haven't confused the issue enough, the point is, this leg is congruent to this. This is congruent to itself, and the angle in between is congruent, so these two are congruent, and you're all done. Here's a problem we're gonna, this is reasoning, that means think your way through it. I find it much easier if I draw a picture. I mean, you can probably picture this mentally, visualize it, so to speak. I'm not too good at that myself. Unless I'm hungry. I can visualize food if I'm really hungry. I see pizza everywhere when I'm starving. But this kind of stuff, no. I do a lot better if I just draw myself a picture. So what's all this mean? M is the midpoint of PQ. Well, gee. Maybe I better label this thing, huh? How about RMP? That sound good? As I said, I'm really bad at visualizing this stuff. I started to draw a triangle, and then I was going to draw another one, and realized that we have RM here and RM here. That means they share a side. So here's RM, and then here's the point not on that line, and here's the other point not on that line. Which turns into two triangles with a common side. Explain why these two were congruent. If RM is perpendicular to PQ. Well, I didn't draw that too well, did I? I'll pretend that's the right angle, maybe. See what happens. If that were a right angle, and M is the midpoint of PQ, well, we wouldn't write it. They would not have written it that way if this wasn't intended to be a straight line. So, did I mess up or what? That's 2 or 3 times I have mentally visualized this incorrectly. This is why I draw pictures. You might be better at this than me. You can get by without it, but me, I need to draw pictures or I'm lost. Now this is what they're telling us here. RM is perpendicular to PQ. This diagram fits all the verbiage now. We have a common side, RM. We have these 2 points off this common side, which form 2 triangles with a common side. And RM is perpendicular to PQ, so that these are both right angles. This here is a bisector, so we know that this leg is equal to this leg. What about this? We don't really need to worry about the hypotenuse, do we? Or hypotenuse? Hypotenuse? Is it hypotenuses or hypotenuse? Well, you can look that up. This is congruent to itself. So we have a side, an angle, and a side which are congruent. And what does that mean? It means the two triangles are congruent by the side angle side postulate. See, once you draw a picture of what's going on, I mean to say, an accurate picture, you can draw the kind of pictures that I drew to begin with, and you'll be twice as lost as if you never even drew a picture. So, draw an accurate picture, and it's real easy to see what's going on. Doing it just in your head, well, you might do okay. You saw how well I did in my head. I had to draw it 3 different times before I got it right. Well, this one's kind of cool just because it's so weird. I mean, look at this bizarre shape. If I was a student and looked at this, I'd be intimidated. In fact, I'm not a student and I'm already intimidated. So let's just mark off what all this says. In other words, we have some kind of a drawing here. Now let's start marking our drawing according to what's written here and see if anything jumps out at us. We've got AB is congruent to AC. That's this here. And this. Maybe if I mark it, try to remember we're talking about this whole thing, not this short part here. AD is congruent to AF. Okay. AD is perpendicular to AB. Huh? AD is perpendicular to AB. Okay, that makes sense. And AF, that's this, is perpendicular, I bet, to AC. Yes, indeed. So, we've got that. Now, can we conclude that A C D, oh, I see, okay. Yeah, they're really messing us up here. These are overlapping triangles, I believe. ACD is congruent to ABF. So now that we have these drawn in here, got this AB and AC. Put the little hash marks there. Hash marks, right triangle symbol. They're asking about, I tried to color these in so you could keep straight which triangles we're talking about. Maybe I should just redraw them over here. Well, we got this. We'll try it for now. Triangle ACD, that's this big one here, and then ABF, that's this one here. So you see we've got the long base here and the long base here, and then these two. So what do we have? Well, for this triangle here, we have that, and this one, this side is congruent to this side. This angle this is a large angle here. It's an obtuse angle. See, this is a right angle right here, but this is the angle made with one side of one triangle and another side of another triangle. This side and this side are not part of the same triangle. So it's tempting to say, well, we got SAS, but no, we don't, because this is not one of the interior angles for this triangle. It's just the angle made by the intersection here. But it is still useful. Why? Well, this angle here, FAB, what is it? It's made up, just this line right here splits it. It's this right angle plus whatever this is, which is angle BAC. This angle over here is a right angle. I'm talking about this large one now, this obtuse angle, which is part of this triangle here. This is the right angle, the 90 degrees, plus BAC. So they're both of these angles are 90 degrees plus BAC. That's how you know that this obtuse angle is congruent to this obtuse angle. this side's congruent to this side. I redrew what's going on up here, over here, and used two different colors for the triangles to make it more obvious. I don't know about you, but this looks pretty cluttered to me, and frankly, all this stuff is kind of confusing me. Not that that's all that difficult. We have AB and AC are congruent. That's these two. This is one leg of this triangle, and this is a leg of this triangle over here. Okay. Now, AD and AF, that's this one and this one. They're congruent. So we have two sides that are congruent. So far, so good. If the angles in between were congruent, we'd be all done. So what are the angles in between? Well, this angle here, that's this whole thing here, that's the angle between this side and this side. And that is a 90-degree angle plus the measure of angle BAC. This angle over here is 90 degrees plus the measure of BAC. Well, they're both 90 plus the same thing. I guess I should write that out. If we write it out, it's even more obvious. We have measure of angle CAD is this right angle plus BA, or in this case CAB, doesn't matter, you can write it either way. BAC. Down here the angle of CAD is 90 plus the same thing. So these two are both equal to something else that are the same. These two are both equal to the same thing. So you can call that the transitive property, which makes these two equal, or the substitution property. You can substitute that in for that. I think I've pointed out about 100 times that they're extremely related. So you can conclude, and this is the reason. Of course, you can always conclude. What I meant to say was you can conclude that the two triangles are congruent. And that would be, of course, the SAS postulate that makes it work. Now here's one that, even though it's multiple choice, doesn't look all that easy to me. Well, before we start picking things, let's draw in what we know, what we can figure out from what's given here, and see where it takes us. For instance, we've got 70 and 70 here, so this angle here must be 40 degrees, right? Because they have to add up to 180. On the other hand, what have we got here? I may not need it, but this is a straight angle, and we've got 1, 2, 3 angles that should add up to the straight angle, which is 180. So 70 and 40 is 110. It looks like this is 70 also. Well, that's interesting. Well, we have this side, according to the diagram, is congruent to this side. This side's congruent to this side. And we just figured out that the angle in between is congruent. So this triangle here, this AFD, is congruent to ACD. That's this line right here. But we don't know if we've got enough yet. Now that we have that, what else can we show? Well, how about this triangle here that goes from A, let's see here, yeah, ABF, and then this one, which goes from AC AE. So we have this triangle here, AED, and this triangle, ABF. I say they're congruent. Why would I say something like that? Well, we have this side is congruent to this side. And since we already showed that these two triangles were congruent, I was able to put the double hash marks up here because that shows that this side is equal to this side because these two triangles are congruent. So I was able to write these in myself. These weren't an original part of the diagram. I drew those in from this statement here. So we have these two sides congruent. Now this here is 110. Okay, no big deal. But if this is 70, these are the two congruent sides, just like these are the two congruent sides. And this is an isosceles. Well, we don't actually know that yet. That'll come up in the next section. Right now, what we know is, since these are congruent and these two angles are 70, these two angles are 70, and this angle up here, of course, would be 40. We may not need to know that. But if this is 70, then this one here must be 110. Why? Well, this is a straight angle. And this is cut up into two angles, one of 70 and the other one has to be 110. Well, what good does that do? Well, these two are vertical angles. So, we know that this angle is 110. Now what do we have? We have this side is congruent to this side. We have this side congruent to this side. And this angle in the middle here is 40 plus 70. That's 110. Well, this angle in between, that's 110. So this ABF triangle, we can now see is congruent to AED. We couldn't do that right off the bat. It's tempting to say the two triangle congruences we need to show are ABF and then AED. We need to eventually show that, but we can't do that until we show that these two triangles are congruent. That gives us that this side is congruent to this side. Before we did that, we couldn't do the second part, which is that ABF is congruent to AED. Now that we have that, because this side and this side congruent, this side and this side, and the angle in between them. Now, well, what side and angles are left over? Well, this side corresponds to this one. So this must be congruent to this one here. So that's 40. Pardon me, I said that wrong. This angle here is congruent to this one, which we know is 40. Why? Well, this segment here does double duty. It's part of the triangle AFD, but it's also part of the triangle AED. So this angle here is part of both triangles. And because this triangle is congruent to this triangle, we know that this angle is 40 degrees. This one down here, sorry, that wasn't relevant. I misspoke. That's how we know. This is the corresponding angle, which must remember, congruent triangles, the corresponding angles have to be congruent. Here we have 110, 110. Here's the 40 and the 40. So what's left over, I think, is 30, right? We got 40 and 110 is 150, so there's 30 left over here. 40 and 110 is 1. Oh, and there's 30 left over here, of course, because they're congruent. And in fact, we could have just said that in congruent triangle, corresponding angles are congruent, and these two are corresponding angles. We didn't really need to compute all these actual numbers. I just did it to show you what was going on here. It says multiple choice, but it's really multiple step. First we show two triangles are congruent, use that congruence to show two other triangles are congruent, and then show that the corresponding angles must be congruent. Okay, that's about it.